All right, everybody. So today we are going to be covering the notes for section 9.4, graphing exponential and logarithmic functions. But in order for us to do this lesson, we actually need to start on page 14 to review one concept that we have from our past. And so with this lesson, we're going to be graphing logarithms, but you have to understand that logarithms are related to exponential functions. Now, this is something that we've already done in the past before. Notice this is what we call the parent function. Yes, one was exponential growth, the other one was decay. But when you're working with an exponential function, and this is the parent function, you have to understand that the parent function always goes through the same 2 points in an exponential function. And that's this. They always go, look at that. I'm going to make a little table here. Exponential functions always go through the point. So we're going to make a little table here in between the point 0 and 1. Notice how they both hit that value right there, 0, 1. But then they also have a point that's in common, and that's this one right here. That's a value of 1. And the idea is if you were to plug in a power of 1, then that means this value is just going to be b. So these are the two very generic points that all exponential functions go through, all exponential parent functions. Notice there's no a value. We only have a b to the x, nothing else. And so if you notice, the same thing will happen on this side. My point is 1. And of course, it's going to hit the value of b. It's hard to tell, but it's going through 1 and b. The reason the b is so small, remember, it's a fraction. That's why this is exponential decay, because when you're dealing with stuff like this one, with exponential decay, you're going to get some very small numbers with these values. Same thing here. This one was exponential growth. This would be the airplane taking off right here, right? It's kind of like an airplane taking off. This one would be kind of like an airplane coming in for landing. But when we talk about taking off and coming in for landing, it means you need a road for it to take off from, or you need a road for it to land on. And that's where the asymptote always kicks in. And so one of the things that we mentioned about an exponential function is that they have horizontal asymptotes. They both do. So the horizontal asymptote, I'm just going to cut it short there. The horizontal asymptote is the x-axis, otherwise known as y is equal to 0. So you see y equals 0 is the horizontal asymptote for a parent function of for an exponential function, but most precisely for the parent function. Now, one of the things that we've learned so far is that if I want to get rid of an exponential, well, then I'm going to go with log form, and vice versa. If I want to get rid of logs, well, then I have to go exponential. So we go back and forth between them. And that's why one of the things that we practiced last week was how to find the inverse function. By finding the inverse function, we know that logs and exponentials are just the kind of the opposites of each other, and they cancel each other out. And one of the things that we did when we did an inverse is we were switching the x and the y before we actually found the inverse. Well, remember, we're going to use that concept for a log here. Whatever my x and my y are, I'm going to switch them out. And when I switch them out, that's going to give me the graph of a log. Same thing with a horizontal asymptote. If it said y equals 0, but I'm doing an inverse means that every x becomes a y, every y becomes an x. So this horizontal asymptote will also change. It's no longer going to be horizontal. Since it's going to say x equals 0, it's going to be more of a vertical asymptote. Now, yes, we have all the rules below here, things that we've talked about in the past, about moving up, down, left, right, but we already have all of this in a previous note. In fact, this is from section 9.2 that we already covered. So for today, let's go back to the start of this note. We're going to be talking about graphing exponential and logarithmic functions. Now, exponential we've done, so we are going to concentrate on log functions. And I'm going to try to show you maybe the easiest technique possible for this. So if you notice, this is what we call our parent function. And when you look at the parent function, well, look at the graph and what it's doing. Notice how the graph is heading up and it does get bigger very slowly, but it does continue to go up. Or it heads down, and notice it continues to drop, but at a very slow rate. Now, this is very different than the exponential function. In fact, check out the point that it's going to go through. This right here, just like this one, is the point 1, 0. And if that sounds familiar, well, that's because when we did the exponential, it was 0, 1. Remember, we said we were going to switch our x's and our y's. So when I'm looking at this table for both of these, my table so far says 1, 0. Remember, same thing with the exponential. It was 0, 1. This one is 1, 0. And of course, the other point that's going to be very important for us is this one right here. Here's my b value, and it goes up to a value of 1. And so because of that, my point is always going to be a b to the 1. Now, remember our b values here. Our b values are less than 1. So it's actually not going to be on this side. My b value is going to be over here. And when I go up, no surprise, that will be a value of 1 right there. So these are the points that all logs go through. 1, 0 and b1. These are the 2 points that all parent log functions will go through. Now remember that b value could be any number. It could be the e, the 10, the 5, 7, whatever number they want. That's the number we would end up putting here. So for instance, look at the b value for this problem. The b value here for this parent function, notice how there's no adding or subtracting of any type. Look at what my table would be. When I'm drawing this, based on what we just said, it would be 1, 0 automatically and base 1. Well, my base is 3, so we're going 3, 1. Look at this one. Even when your base is a little strange, like 2/3, doesn't matter. Look at our basic table. It's always going to be 1, 0. They all go through that point. But as we mentioned, the next point is always whatever your base is, even if it's as weird as 2/3, with a 1 as your y value. And then the only last thing to mention on these is yes, there is an asymptote. Now remember, previously, this was our asymptote before, right? That's why our graphs would land on this line or take off from this line. But notice how the log is actually making contact. They're not supposed to. Well, that's because we no longer have a horizontal asymptote. We now have a vertical asymptote. And the reason for that is we said my x's and my y's had to switch. I switched them for my point. Well, I also have to switch it for now our vertical asymptote. Remember, a vertical asymptote or any asymptote is like a wall that your graph cannot go through. And so my vertical asymptote is now x equals 0, not y equals 0, because we switched the x and the y. So again, a very different way of looking at it. The log function is very different in this case. Now, we are going to be making some of the same moves we've done before. Notice how there might be an a value. This is where we're going to be moving to the side. So remember, if it's inside the log, notice they have to use parentheses. If they use a parentheses and they put a number in there, you got to remember, we're going to think opposite. That's definitely true for these. We're going to think opposite. And of course, if you have your k value, look at where your k value is. This is outside the parentheses. Then we're just going to move up or down. But the note we have to make is this. K is not inside a parentheses. If it's on the outside of a parentheses, that's how we know it's up and down. But that's a common misconception. People kind of mix up the left and right and up and down sometimes. Here must be in a parentheses. All right, so we are going to be taking some basic steps here. Oh, I almost forgot. Vertical stretch and shrink can still happen if there's an a value in the front, which I don't think for these problems that we're doing, we're going to have that issue. But just in case, just know that if your a is bigger than 1, we have a stretch. If you have a vertical shrink, it's because your a is between the 0 and the 1. But once again, I don't think we do have that situation coming up in our problems. So here we go. When graphing a logarithmic equation, number 1, all right, some basic steps. Set up a table for the parent function. Number 2, draw the parent function, which, by the way, includes the asymptote. So we draw the parent function and the vertical asymptote. Number 3, after we draw the parent and the vertical asymptote, describe the transformation. So remember, this is what we mean about moving left, right, up, down. So describe the transformation, and finally, draw the graph. After the transformation, of course. That's why we describe the transformation, draw the graph that follows, we'll say, the transformation. All right. All right, so let's give this a try. Now, if you notice on example number 4, it does say we are going to be graphing, of course. We're going to graph the log function. We are going to state the asymptote, the x-intercept, and then we're going to describe the transformation. So here we go. First of all, well, as soon as I see this, I notice one thing. Look at that. It's inside the parentheses. So according to our note, which you can kind of see here, it's inside the parentheses. So when I'm looking at this bottom corner over here, x minus h means I think opposite. That means we're going to be moving to the right. And I'm going to move to the right 3 spaces. All right, so I'm going to keep that in mind. Actually, we can already write that down here. We're going to move right 3 units. All right, so now, next thing, we're going to talk about the parent function. Well, remember, the parent function is y equals, instead of f of x, we'll call it y, log base 3 of x. Notice we do not bring in the negative 3. That's why I like highlighting it, because those are the things I will not bring into my parent function. Notice the parent function is just the log and the base with the x, and then that's it. So because this is the parent function, here come the original 2 points. 1, 0, and then base 1. Well, my base is 3. So 3, 1. And because my base is a 3, we know this should look like this. It's kind of think of it as growth. I know it's weird to think of it that way because it comes from the bottom there, which means it better look like this. And if it doesn't look like that, we know something went wrong. So here we go. 1, 0, 1, 0, 3, 1, 3, 1. And remember, before you actually draw it, you have to remember there is a vertical wall for now in this spot right here. So there is a vertical wall known as our asymptote, and then this is the graph. And then it just kind of keeps going. Now that's the parent. That's why I made it kind of light. I didn't use a dark color because it's not my final answer. But now it's time to talk about the moves. Well, look at the moves that we said we were going to take. I'm going to move to the right 3 spaces, but remember, before you do that to the points, there's one thing you have to move as well, the asymptote. And because my asymptote is going like this, right, up and down, and I'm going to move it to the right 3 spaces, you see how the asymptote is also moving. So we're going to have a brand new vertical asymptote, which will now be located 1, 2, 3 right here. This is the wall, right? The imaginary wall that our graph is going to get closer and closer to. So my vertical asymptote is now x equals 3. Now, the note that we want to write to ourselves is this. We will get a new vertical asymptote. So we're going to get a new vertical asymptote when we shift left and right, left or right. And because we said we were going to move to the right, well, guess what? That became our new vertical asymptote once we said this thing was going to move to the right 3 spaces. So now I'm ready for my points. Now my point said we were going to move everything over 3 to the right. So 1, 2, 3, 1, 2, 3. There it is. You see, we're just over that wall there, that vertical asymptote. And just like that, I'm now ready for my graph. Remember, it gets closer and closer to that wall, and then it just kind of makes that turn. And just like that, there's my answer. And look, it's very easy to spot that my x-intercept, look where we touch the x-axis, right at positive 4. So my x-intercept is 4, 0. No work needed for that because we can actually see what it was. And there it is. This is how we draw our logs using the parent function as a starting point. So let's try it again. Now, example number 2. As soon as I see this value and this one, those are the two I have to watch out for. It's inside the parentheses. So right away, look, it's actually right here. You can see it. It's inside the parentheses. So that's left and right. And because it's positive, I'm going left 2. But then I also see a -1. Notice how it's not in the parentheses anymore. It's off to the side. When it's a -1, well, then I'm going, in this case, down 1. And, well, these are really the only 2 moves that I'm creating for this problem. So I can already describe my transformation. It's going to be a shift left 2 and down 1. So you see, I already have my description ready to go. But now let's talk about the parent function here. Now I do notice, remember, this is kind of your parent function right here without all the highlighted stuff. Look at that 1/2. That's kind of decay. So yeah, that's kind of like decay, which means when I draw this graph, it kind of has to look like this. Like it's dropping. As I go to the right, it's going to be dropping. All right, but let's talk parent function. So here come my 2 points for the parent. Well, actually, y equals log base 1/2 of x. Remember, none of that yellow highlighted stuff, just this. So with that said, here we go. Here comes my 2 points, x, y. My first point, remember, for a parent, it never changes, 1, 0. Then I need the base, which is 1/2, or 0.5 if it's easier, comma 1. Those are my 2 points we always work with when we're working with the parent function. So now we're ready to draw this thing. Remember, we have an original asymptote right here, just waiting. My 2 points are 1, 0, and this is where it gets interesting, 1/2 and 1. Notice how close they are to each other, but we said it was going to drop, and that makes sense. Look at this. It's going to drop, and yeah, it'll continue to drop very slowly, but it's starting to look like this. Okay? Remember, don't have it just shoot straight down all of a sudden. No, it's got a curve, slightly dropping every time. But now it's time for our moves. Now, remember the moves we said were going to happen. The first move we said was we're going to move everything left 2 now. Remember what that means too. That means the asymptote is also moving. The original one was right here. It is now moving to the left 2 spaces. So as soon as we said left 2, that automatically affects the asymptote. So x is -2. There's the new asymptote for this problem. And now we're going to move our points. Now remember, We're moving our points left 2, down 1. So we are taking 2 steps. Left 2, 1, 2, and down 1. Down 1. There is my brand new point right there. And this is the only one to watch out for. You are going left 2. Notice how we're kind of in the middle, and down 1. So we end up right here. Notice how they're the same distance apart from each other. And then here comes the graph. And it just kind of drops and drops and drops. But there's my answer. Now I need an x-intercept, and we can't see it here. Look at that. My x-intercept would be right after -1, but not making it all the way to -2. So my x-intercept is -1.5. We can use decimals, comma 0. So again, this is how we take our time in drawing these graphs for logarithms. All right, now, once you look at the other side on page 14, here's where you have the you try problems, but I want to do this one with you as part of the notes. And so notice what it says. I do have a +4 involved in this problem. The question is this: is that +4 in a parentheses, yes or no? The answer is no, of course. Only the x is part of the log. That +4 is separate, which means one thing. This thing is going to move up 4 spaces. There is nothing happening as left with left or right, which means this is why I wanted to show you this problem. There's no left or right for this situation, which just means one thing. When you have no left or right, well, then when it comes to our vertical asymptote, there's no new one. There will be no new vertical asymptote, which means it's going to go back to the original of x equals 0. So my vertical asymptote, I can already start drawing it. Since there is no left or right, this is why I wanted to show you this problem. We're not going anywhere then. That's going to be my vertical asymptote for the rest of the problem. We also said we're going to move everything up 4. So we're going to shift up 4. And remember, even if you said, oh, but it is going to move, I'm going to move it up 4 spaces. Notice how it stayed in the same spot. That's why the vertical asymptote is only affected if you move left or right. Now, we're ready to get started with our points. So first I'm going to start with the parent function, which is log base 2 of x. Remember, no highlighted numbers, no extra values. So here come my points. The first one is a classic 1, 0. The second one is b, comma 1, right? But we already know what our b value is. I just realized that there. It's a 2. Then it's a 2, comma 1. Remember, those are always going to be the 2 points. Here I have the exponential to guide us. Remember, we switched everything. Well, there it is. Look at that. Look at that switch. We switch our x's and our y's when we do inverse. So I'm going to start with the parent, of course. The parent goes through 1, 0, and then 2, 1. And yes, because this is a 2, this is you can think of it as growth, which means it kind of goes like this, right? It's growing. So here's the parent function. Just a generic. I know there's a couple points we could probably find. Just want to show you the most basic way of getting an idea what they look like. But we said everything was going to move up 4 spaces. All right, well then, 1, 2, 3, 4, 1, 2, 3, 4. And so just like that, we have these brand new points here. And then here's my graph. Remember, it gets really close to that wall, and then it just slowly climbs right after. But it keeps getting closer and closer to that wall. It almost looks like it hits, but it never really does. So there's my graph. Now, the only issue that this created is I have no idea what that x-intercept. Remember, this is the parent. That's not the one I'm looking for. I'm looking for this one right here. So to find an x-intercept, remember, when I write it as a point, my y value is always 0. So for my x-intercept, make y equals 0. So here comes my equation. Look, I know it says f of x. That is your y. 0 is equal to the log base 2 of x plus 4. And now we're going to bring in our skills that we've been practicing. I'm going to subtract the 4 because we don't work with that. So now I have negative 4 is equal to log base 2 of x. And this is what we've been practicing, everybody. I want to turn this into an exponential. I want to get rid of the log because I'm trying to get the x by itself. So look at what it says. 2 to the negative 4th power is equal to x. 2 to the negative 4th is the same as 1 over 2 to the 4th. And of course, that becomes 1 over 16. That's why it's such a small number. Look at that. So close to that 0. So it's 1 over 16, comma 0. But that would become our x-intercept for this problem. Now, be very careful. You only have to do that if you can't see the x-intercept right off the bat. But all it takes is a little circle method like we've been doing in the past to get us to that x-intercept. Now, the next thing we're going to do to finish off our notes, you have that u-try problem you don't have to worry about. We're also not going to be worried about graphing this type of function because we've already practiced these a lot. The only thing I do want to mention on these actually is this. Instead of drawing, because it's already a lot of notes here, we're going to talk about the change. How did this one go to this one? Well, again, I want to talk about the transformation. So here's the only thing I want you to work on with these. It says 4 to the x, and then it says 4 to the x plus 5. The plus 5 is not in the power, which means this is a shift of 5 units up because it's not in the power. But yet, when you see an exponential like this one, now we have a number in the power and we have a number here. This is all I need you to practice for some of these problems because all they're going to want is a description. X minus 1, then I'm going to the right one because we always think opposite when it's with the value of x. And the positive 2 is not in the power, well, then we go up 2. Again, we're not going to practice a drawing, just reading graphs. That's what's important first. Look at these two down here. If this is my exponential function, look at what they want me to do to it. All they did was add a minus 3 in here, but it's in the power, so that means I'm going to shift 3 units. But of course, it's in the power. I got to think opposite. Then I'm going to the right. And then there's this one where they throw in a log for us. If you're working with a log, be very careful and see if it's in a parentheses or not. This is definitely in a parentheses, which means how is this one changing this one? That means this one right here, all that's going to happen is we're going to shift to the right 3 units because the 3's on the inside and we're going to be thinking opposites with them. Now, all right, so that brings us to the end here. The last page, all they want us to do is, again, continue practicing how to describe the transformation and how that affects our graph. Now, remember, there's a difference between exponential and logarithms. Exponentials have horizontal asymptotes. Logarithms have vertical asymptotes. So depending on the move that we make, it's going to affect that graph. So if you notice, this one right here is an exponential function. An exponential function has, right, the landing, if you want to think of it, a landing strip. And because this is growth, it would look like this. It's taking off. But they have horizontal asymptotes. So when they say x plus 2 in the power, then that means this is going to shift 2 units. And now we need the direction. Well, it's in the power. So we're going to move to the left. We think opposite. 2 spaces. Well, remember, if my asymptote is like this and I move it to the left, let me do that. There it is. It doesn't go anywhere. It's the same spot. That's why it says give the equation of the asymptote. The horizontal asymptote is then, remember, it's horizontal, so we say y equals 0. Moving left, not up or down, is the original asymptote of y equals 0. Left or right has no effect on this type of equation. But look at number 16. This is also an exponential function, which means, yes, I have a horizontal asymptote. This is growth right here. Sorry, because it's positive, it's growth because of that, not this. So we know it's taking off like that. But look at that minus 2. That minus 2 is not in the power. So we're going to head down 2 units. And remember, moving up and down in the exponential world means the asymptote is going to move on us. So because we're moving down, we're going to have a new horizontal asymptote. And the horizontal asymptote would be y equals -2. Why the negative? Because we moved down 2 spaces. So remember, each function, that's why we have to tell the two apart. They each have their own type of asymptote. So that's why when we look at number 17, yes, this is a log. I can think of it because of the 3 right here. I can think of it as growth, but because it's a log, it has a vertical asymptote. And because we see it as growth, then we know that it's going to take off by heading up. But we do have a vertical asymptote. And here we go. As soon as I read this, that plus 5, that's the question. Well, it's not in a parentheses, so we're going to move up 5 units. But remember, if I move a line that's up and down and I just move it up, it doesn't really go anywhere. So because I moved up, there's going to be no change in my vertical asymptote. You see, we got to keep it clear there, is x equals 0. It's the original. It didn't change because I moved up 5. So my vertical asymptote stays the same. Notice the difference. Horizontal's y equals, vertical x equals. All right, let's see. Let's keep going with this. See if we get the idea. All right, so here we go again. So here I have a log. I see the 3. So yes, we know it's going to be like this. And it's a 3, so it's going to be growth. All right, so that's what I'm looking at. But this time, look at where they put the 5. The 5 is located inside the parentheses. So because it's inside the parentheses, that just means one thing. Being inside, I am thinking opposite. So I'm going to basically go left 5 units. But now remember, look at this asymptote. If I'm going to go left, that line is actually going to move. So because I'm going left, I'm going to have a new vertical asymptote, which is x equals, and because I went to the left, the negative direction, -5. And again, that's the connection we're trying to make with this. To make it easier, we want to make sure we understand how to read and how important it is to know where the values are. All right, let's try it again. Hey, same one. Look at that. It's a 3, so it's growth. And because it's growth, yes, here's the asymptote. There's the growth. It would look like that if I were drawing. But here comes the issue. We're going to move. There's a -2 and there's a +1. The -2 is going to move it right 2. The +1 is going to move it up 1. This is in parentheses. This one is not. This is up or down, right and left, thinking opposite. But out of these two, who's going to affect the vertical asymptote? This one's going to affect the vertical asymptote because I'm going to have a new vertical asymptote. And that vertical asymptote, because I went to the right, that vertical asymptote is simply x equals +2 because we moved it to the right, but we did have a new one. But remember, only moving to the sides can affect the vertical. Moving up and down doesn't do anything to the graph. And finally, they're going to try to throw us off here by giving us an exponential all of a sudden. Here's the exponential. Exponentials have horizontal asymptotes, and because this is growth, we're going to see that plane take off, basically, or this rocket, whatever you want to think of it as, just taking off. But now let's look. -1 and +4. The -1, it's in the power. We got to think opposite. We're going to go right one. The +4 is going to move it up 4 spaces. We don't think opposite on that. Give the equation of the asymptote. Well, remember, right and up, this is a horizontal asymptote, so moving it to the right doesn't do anything, but up and down does. So this is who's having an effect. We have a new horizontal asymptote, and that new horizontal asymptote is, because it's a horizontal line, y equals up 4, +4. And just like that, we have our asymptote for this problem. All right, so with that said, you do have a homework assignment that you're going to be working on. Because you're graphing, it's not really going to be on big ideas. So we are going to have a worksheet. And if you notice, you kind of have all these old school questions for review because we do need to start getting ready for the test. Here you have one where you're going to be graphing. Look at that. That's just a parent function, hint, hint. And then, of course, we also have these here. Now, I am going to mention one last thing. This is from your homework, but I think I should mention it. Remember, there is a base of E right there, and E is 2.7. So there's no big ideas. It's just on paper today. So E is 2.7. Now, look at what we have to do here. This one means I'm going to go up 4. All right, but it's a natural log. So here we go. X and Y. Here's the parent. Y equals the natural log of X. And then my original point is 1, 0. Remember, that never changes. But then here comes the other one. It's B, which is E, aka 2.7, and 1. So when I draw this out, don't forget, yes, I'm going to have an asymptote right here. 1, 0, 2.71. So 2.7, look at that. There's E, and 1. So there's the parent function. All I'm going to do now is I'm just going to move it up 4 spaces. So 1, 2, 3, 4. Remember, the asymptote is not changing. And yes, even though you're stuck in the middle here, 1, 2, 3, 4, there is our graph. They did say to name a few things. First of all, I went up 4. Next thing, they said name the asymptote. Well, this is a vertical asymptote, and if you notice, it didn't go anywhere. It's still the classic x equals 0. Remember, I didn't go to the sides. And they did say they want the x-intercept for this problem. Now, x-intercept, I have no idea. That's why I wanted to show you at least this one. 0 is equal to the natural log of x plus 4. So all I have to do is take away a 4. -4 is equal to the natural log of x. There's the e, and here comes that circle method. E to the -4 is equal to x. So as weird as that looks, that's how I'm going to leave it. I don't want a decimal out of this. So my x-intercept is e to the -4, comma 0. And there's my x-intercept. So I bring that up because you're going to do something very similar on number 12 with the natural log. So now you have one less problem to do for homework. All right, with that said, everybody, have a wonderful day. Hope to see you soon, but have a good one.